Annealing is not only a broad and generic term, it's also one of the most misunderstood processes in metal manufacturing. The summary definition of annealing is heating to a suitable temperature followed by a cooling at a desired rate. In this module, we will discuss the process and benefits of annealing as well as its impact on product performance. Here's Ed Blessman with some additional insight on annealing.
Hello, I'm Ed Blessman, Technical Development Manager at Plymouth Tube Company. Annealing can solve many issues in stainless steel tubing and is used to homogenize the microstructure, achieve uniform mechanical properties, and relieve internal stresses which can lead to premature failures. Welded tubes should always be annealed after welding, and all tubes should be annealed after each cold working operation to achieve maximum ductility and corrosion resistance. The improved consistency provided by the annealing process allows tubes to be more easily manipulated in secondary operations, such as forming, flaring, or shaping. When applied correctly by an experienced manufacturer, the annealing process is an important part of a corrosion prevention strategy. For different alloys, the time, temperature, and cooling rates may vary considerably. For example, alloys containing nickel and molybdenum require extended time at temperature to achieve optimal results. Alternatively, in alloys like superferritic and superduplexes, the quench rates are critical to avoid microstructural imperfections invisible to the naked eye. Annealing is especially important in applications where low residual stress is required, special corrosion testing is needed, or where high amounts of forming will be performed, such as in hydraulic tubing. Annealing may also be used in conjunction with other processes, like cold working, to ensure that your tube will withstand the corrosive environments they're exposed to and get the job done.
For optimum corrosion resistance, all stainless steel alloys should be annealed after welding and cold working operations are completed. Tubes may be annealed one at a time, in line, or in batches. In-line heat treating is the most common method of annealing stainless steel tubing. In this method, the tube is heated with an induction coil to the desired temperature and then rapidly cooled with either water, convective gas such as hydrogen, or an inert gas such as argon. The heat treatment is performed in-line on the welding mill, usually immediately following the in-line cold working operations. In-line annealing is performed in tandem at weld speed, meaning soak times are kept to the minimum. When induction annealing is performed, the time at which the tube is at temperature is very short. Once the tube exits the coil, the quenching process starts. In-line annealing provides manufacturing efficiencies which can reduce manufacturing costs, provide high quench rate, but there may be trade-offs relative to product performance. The shortened hold time does not allow some stainless steels containing more than 6% nickel to completely homogenize. While you may be able to solution anneal, the remaining segregation can significantly lower resistance to other forms of corrosion. Offline annealing is another annealing process. This is a process that can be refined and adjusted to each alloy and a specific finished outcome. The offline separate furnace anneal provides a significantly longer time at temperature than the inline anneal, typically in the 5 to 10 minute range. This is the time frame needed for full weld homogenization of the alloys containing greater than 6% nickel. The longer hold time provides for greater homogeneity and general corrosion resistance for the austenitic grade steels. This is especially important for alloys with higher nickel and molybdenum concentrations. Quench rates are not as quick as induction anneal. Although sufficient for austenitic alloys, the furnace anneal should not be used for the superferritics and superduplex grades without special qualification testing. Two types of atmospheres are commonly used during heat treatment: bright annealing and open air. These atmospheres can be used with either in-line annealing or furnace annealing. Bright annealing employs a reducing gas atmosphere, such as hydrogen, that minimizes the formation of oxides. Because the thermodynamics of the hydrogen-oxygen reaction are not active at lower temperatures, bright annealing is only effective when the annealing temperature is above approximately 1500 degrees Fahrenheit. Alloys that require a lower annealing temperature, such as TP439 and superferritics, cannot be effectively bright annealed without very special atmosphere controls. To keep the tube surface bright, the atmosphere needs to be maintained during both heating and cooling to temperatures below 700 degrees Fahrenheit. Water quenching is not an option, as the water will cause scale formation. Therefore, bright annealing quench rates may not be sufficient for some ferritic and duplex alloys when corrosion resistance is critical. Since the surface of a bright annealed tube does not develop a thick scale, the final tube surface finishes may be smoother. It requires dry hydrogen atmosphere, low dew point, at annealing temperature chemically reduced oxides keep surface from reoxidizing while cooling. Open air heat treatments allow rapid heat and either forced air or water quenching. This ensures that ferritic, duplex, and heavier wall higher alloy austenitic alloys that have potential for forming detrimental second phases will not be degraded. However, the exposure to the air and water results in a scale on the tube surface. This scale must be chemically removed for optimum corrosion resistance. Some cautions and conclusions. Inline annealing of welded austenitic alloys can result in subpar corrosion resistance in the welds. Alloys can be over-annealed. Stabilized alloys should have secondary phases present. If they have been fully solutioned, corrosion resistance can suffer. Excessive grain growth can harm ductility and formability. Inert gas is not bright annealing. It may be shiny, but corrosion resistance will suffer. Pickling may be required to restore optimum corrosion resistance. Rather than specifying process, it is best to specify performance. Require testing for anneal condition. Annealing is an important part of manufacturing, but without additional qualification, the general ASTM and ASME spec are often inadequate. Product performance expectations are key factors to be considered when defining the alloy of choice and the selection, manufacturer standards, and guidelines.